So, hello everyone and welcome to the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Anna Agore. She's going to talk on solutions of the set-theoretic Yang-Baxter equation of Frobenius-Separability type. Please.
Thank you very much for the kind invitation and the introduction. I'm very happy to join your seminar. So my talk will be based on a joint work with Alexandru Chirvasitu and G. Militaru, contained in the paper you see on the screen, and also on some work in progress, which is not yet available on arXiv. The plan of the talk is as follows. I will start by recalling the context in which the set-theoretic Yang-Baxter equation was first introduced by Drinfeld more than 30 years ago, called Frobenius-Separability equation and its connection to the Yang-Baxter equation as introduced by Drinfeld. Our approach for studying the Yang-Baxter equation of Frobenius-Separability type leads very naturally to some basic combinatorics and even graph theory. So I will recall very briefly the most important notions and results we need. And then we will see certain classification results for various classes of solutions of the Yang-Baxter equation. And finally, if time permits, we will discuss the automorphism groups of these special kinds of solutions of Frobenius-Separability type. So the Yang-Baxter equation appeared in the field of quantum mechanics and statistical mechanics. It grew out of Young's work on exact solutions of many body problems and Baxter's study of the 8-vertex model in the two papers listed on the screen. And just to make sure that we are on the same page, I will just very briefly remind you that a linear map R is a solution of the quantum Yang-Baxter equation if the compatibility on the screen holds. I mean this compatibility where Rij denote the map which acts as R on the I and the J tensor factor and as the identity on the remaining one. The influence of the Yang-Baxter equation in various areas of physics and mathematics can hardly be exaggerated, and I could not possibly do justice to its vast and far-reaching applications. So I will just mention a few of them. It is crucial for constructing integrable models, and as far as pure mathematics goes, the Yang-Baxter equation had a major impact in quantum group theory. In fact, it actually led to the introduction of quantum groups, and it is also important for braided categories, combinatorics, non-commutative algebraic geometry, and so on. The classification of all Yang-Baxter solutions for a given finite dimensional vector space V turned out to be a very difficult problem, and it has up to this point been completely solved only in dimension 2 and 3 by computer in the two papers that you see on the screen. There's also a more general approach, an algebraic one due to Redford, which builds on the famous theorem of Fabeev, Rashtekhin, and Takhtayan. So for this reason, given the difficulty of the problem, Drinfeld proposed a different approach, namely to classify those Yang-Baxter solutions arising from a given basis X of the vector space V, or in other words, studying the Yang-Baxter equation at the level of sets. And more precisely, given a set X, a self-map R on X time X, will be called a solution of the set-theoretic Yang-Baxter equation if the same compatibility as in the case of the classical Yang-Baxter equation holds. This one, except that, of course, this time we work with just maps, not linear operators. So I've included the defining relation of the braid equation in the brackets here. Because in fact, in many papers in the literature, the braid equation is studied under the name of Yang-Baxter equation and vice versa. So you might have seen it in this form. The reason is a simple observation that the two equations are equivalent in the sense that R is a solution of the Yang-Baxter equation, even only if the flip map composed to R is a solution of the braid equation. So it doesn't really matter which of the two equations we consider in the end. Now, just to give you an idea on how difficult the problem is in its full generality, if you write an arbitrary map R as you see on the screen using two binary operations on X, it can be easily shown that R is a Yang-Baxter solution, even only if the three conditions hold. So the problem does seem to be, presently beyond reach in its full generality. So if you look carefully at the defining relations of a Yang-Baxter solution, they do not seem to be amenable to any handling. So the first and the third conditions are some sort of deformations of the associativity condition for the two binary relations, but of course that doesn't say much in general. So for now, as a general strategy, we have to limit to the study of certain classes of solutions, and perhaps to introduce new and more flexible classes of Yang-Baxter solutions, perhaps friendlier to classification. So I will recall the most important classes of solutions that are currently being considered in the literature, and we will often denote a map R as you see on the screen. So the L-axes are called left translation maps, and similarly the L-Ys are called right translation maps, and R will be called a left non-degenerate solution if the left translation maps, all of them, are bijective. So for all elements X in X. And of course, similarly for right non-degeneracy, R is called right non-degenerate if all right translation maps are bijective. Also, it's not written on the slides, but we will call a solution non-degenerate if it's both left and right non-degenerate. A solution will be called unitary if its inverse equals the map obtained by having R act on the second and the first component. The solution will be called involutive if it squares to the identity, and of finite order if its end power equals the identity. And finally, it's called idempotent if it equals its square. Finally, the less well-known concept that I will recall is that of a decomposable solution. So R will be called decomposable if there is a non-trivial partition of X such that R respects the two subsets, and it will be called indecomposable otherwise. And it is really the indecomposable solutions that have received more attention. Now, I should warn you that the terminology might be a bit misleading, at least from a categorical point of view. So if you're thinking of perhaps an analogy with decomposability in abelian categories, like the category of modules, for instance, that would not work, because while a partition on X, as in the definition you see on the screen, will certainly give back solutions on Y and Z, the procedure does not seem to be canonically reversible. So if you start with solutions on Y and Z, it is unclear how a solution on the entire X can be built. Right, there is also the pioneering article of Ettinghoff, Schadler, and Soloviev, which has decisively influenced the development of the theory, which is now overwhelmingly concerned with non-degenerate solutions, satisfying additional assumptions such as bijectivity, involutivity, unitarity, and so on. So the vast majority of papers we find in the literature dealing with the set-theoretic Yang-Baxter equation are devoted mainly to non-degenerate or indecomposable solutions, sometimes with variations on these imposed conditions. The main actors in the approach suggested by Ettinghoff and his co-authors in the paper from the previous slide are the so-called one cocycles, or crossed homomorphisms, as this notion appears in group cohomology or in Schreier's group extension theory. And these are certain maps between two groups G and A, where G is acting on A by automorphisms, for which the condition on the slides is fulfilled. However, the key in the paper by Ettinghoff and his co-author is that he assumes these one cocycles to be bijective, so a condition which is normally not considered in group theory. And in this setting, it was proved that the category of non-degenerate involutive solutions of the set-theoretic Yang-Baxter equation is equivalent to the category of bijective one cocycles with coefficients in a certain free abelian group. However, despite this very nice and general result, the classification problem, even for this class of solutions, is wide open. Nowadays, various equivalent reinterpretation of bijective one cocycles appeared in an attempt to introduce new algebraic structures which are perhaps easier to classify. And a vast literature was developed around these new algebraic gadgets. I will very briefly recall a few of them, perhaps the most important ones. So chronologically, braiding operators on a group were first introduced. So given a group G, these are certain types of bijective cell map on G, which induces a match pair of groups between G and itself. And whenever such a braided operator exists, G will be called a braided group. These braided operators were first considered in the first paper that you see on the screen, but a perhaps more transparent definition, the one that I just told you, was given in the second paper by Takeuchi. Then another important concept is that of a skew brace, which is again equivalent in some sense to bijective one cocycles, but from a slightly different perspective. The idea here is, since we have a bijective map between the two groups, namely the one cocycle, to transfer the group structure from G to A via this map. So skew braces are sets with two group structures which are compatible in some way. And to be more precise, this compatibility is precisely the one cocycle condition which is being carried over on A using the underlying bijective one cocycle. An even more recent related notion are the so-called post groups. These are again groups admitting a second binary operation, which in this case is not a second group structure, as in the case of skew braces, but some sort of an automorphism of the group. So when you fix the first entry of this binary operation, what you obtain is an automorphism of this group. I will not go into further details, but they can all be found in this very nice and rather recent paper. Now, as you probably expect, all these categories are connected in some way, and they are in fact isomorphic. So more precisely, the category of braided groups, the category of skew braces, and the category of post groups are in fact isomorphic. And you can find a more complete picture of the relations between these categories in the paper that I've mentioned on the slides. Now, as opposed to the well-documented theory of non-degenerate solutions, other classes of solutions have only recently been considered. And our work is aligned with this new tendency of studying solutions which a priori do not fulfill the classical constraints like non-degeneracy and so on. Instead, we study solutions called the Frobenius-Separability type, and I will explain a bit what is meant by that. So we will use results by Kimura on rectangular semigroups to prove a result similar to that of Ettinghoff and his co-authors, but with respect to a different class of solutions. And then we will use properties of functional graphs and their associated Davis and Harary numbers and various classical number theory techniques to count the number of isomorphism classes of certain types of solutions. As I already mentioned, the main ingredient of our approach is a class of semigroups introduced by Kimura. And these are semigroups which fulfill the condition you see on the screen. So whenever you multiply three terms like this, the middle term gets killed. As I mentioned, they were introduced by Kimura himself in a paper a long time ago. An easy example is any rectangular semigroup. So a semigroup satisfying this condition is an example of a Kimura semigroup. And these rectangular semigroups include, in particular, the rectangular band, which can be constructed as the direct product of any two non-empty sets with this multiplication. So again, the two middle terms get killed and you are left with just the first and the last terms. Right. Also, the free Kimura semigroup generated by an arbitrary set X has a rather easy description. Namely, it consists of all the 1 and 2 letter words on the alphabet X with the multiplication you see on the screen. So again, it kills everything in the middle and you are again left with the first and the last letters. Now, a few words about the Frobenius-Separability equation, the set-theoretic version a bit more precisely. So for a set X, a map R will be called the solution of the Frobenius-Separability equation if it fulfills the two equalities on the screen, namely these two, where, as before, the Rij's denote the maps obtained by having R act on the position I and J. And it can be very easily observed that any solution of the Frobenius-Separability equation is automatically a solution of the Yang-Baxter equation. And this will be called solutions of Frobenius-Separability type. The linear version of this Frobenius-Separability equation was introduced for the first part in the work of Beidar, Fong, and Stoller in their paper on Frobenius and Hopf algebras. The equation was then further investigated by Canapellion and Militaru under the name of Frobenius-Separability equation. This is where the name comes from, and it is motivated by the fact that defining a Frobenius, respectively a separable algebra, is equivalent to finding a solution of this equation, which moreover fulfills the normalization Frobenius condition for in the case of Frobenius algebras, respectively the separability condition in the case of separable algebras. So our goal is to describe and classify all solutions of Frobenius separability type. Some generic examples are the following. If X is a rectangular semigroup, then R, defined as you see on the screen, is a solution of the Frobenius of Frobenius separability type. Other generic examples can be constructed as follows. So for any self-map X on F, the map Rf defined by first switching X to Y and then applying F on the second component again gives you a solution. Also, if you have an idempotent self-map, then if you act with F on both components on a pair XY, then what you obtain is again a solution of Frobenius separability type. We will see later on that these two examples cover certain classes of solutions. So we want to describe, if possible, all solutions of Frobenius separability type. And if you write down again, if you write this down again, it can be easily seen that a map R, which we denote again using two binary operations on X, is a solution of Frobenius separability type if the three conditions on the screen hold. Luckily, these are in some sense nicer than the one we've seen for the general solutions of the Yang-Baxter equation. And I claim that that these are nicer because of the first one, which implies that that the binary operation denoted by the small dot is in fact the Kimura semigroup structure on X, and we will see that in fact this observation will make our life easier. So we will be able to express any solution in terms of a Kimura semigroup structure. And to this end, we need to introduce the following. So a quasi-endomorphism of a Kimura semigroup is the self-map on X satisfying this compatibility. Obviously, any endomorphism of a Kimura semigroup is also a quasi-endomorphism. And moreover, another example, any module-like map, and by that we mean, again, a self-map on X which satisfies this condition. This is again a quasi-endomorphism of X. Now, the structure theorem for solutions of Frobenius separability type reads as follows. Any such solution is induced by a Kimura semigroup structure on X together with a quasi-endomorphism, and the corresponding solution takes this form. This has implications at categorical level as well, in the sense that a certain category of Kimura semigroups called pointed Kimura semigroups will be proved to be equivalent to the category of solutions of Frobenius separability type. More precisely, we consider the category whose objects are pairs consisting of a Kimura semigroup and the quasi-endomorphism, while the morphisms in this category are just semigroup morphisms which respect the quasi-endomorphism. So this compatibility is fulfilled. Next, we consider the category of solutions of Frobenius separability type. This means that the objects are solutions of this type, and the morphisms are just maps between the underlying set, which behave well with respect to the considered solutions. In this setting, two solutions of Frobenius separability type will be called isomorphic if they are isomorphic as objects in the aforementioned categories. And for a given such solution, we denote like this its automorphism group in the category of solutions. And the automorphism group of a given solution will be discussed in more depth in hopefully in the last part of the talk. So it turns out that the functor which sends a pointed Kimura semigroup to its corresponding solution of Frobenius separability type is in fact an equivalence of category. Another result of a categorical nature is the following. So the category of Frobenius separability type solutions is a reflective subcategory of the category of all solutions of the Yang-Baxter equation, which means that the inclusion functor between the two categories has a left adjoint. This can be very easily obtained from the famous Sprague's adjoint functor theorem, or rather by one of his corollaries on varieties of algebras. And in fact, it turns out that any class of Yang-Baxter solutions which are definable by equations involving the solution R. So this includes unitary, involutory, non-degenerate, idempotent solutions. They are reflected in the category of all solutions of the Yang-Baxter equation by the same argument that we used here. Next, we deal with more concrete classification results for the Frobenius separability type solutions. As I mentioned, some of the ingredients that we need are combinatorial, and I will recall them briefly when they are needed. So the first class of solutions that we look at are the ones that receive the most attention in the literature, namely the non-degenerate ones. So, for instance, the right non-degenerate Frobenius separability type solutions, which I remind you, it means that all right translations are bijective, are of this form, right? And for some bijective self-map F on X. And moreover, if X is a finite set with n elements, then the number of isomorphic classes of all right non-degenerate Frobenius separability solutions on X is equal to Euler's partition number of n. The Euler partition number was introduced by Euler itself, of course, a very long time ago, and it is so it is meant to count the number of all possible partitions of an integer n. There is a vast literature devoted to its study in number theory and combinatorics, and it includes generated functions and asymptotic formulas for computing it. What is important for us is that P of n is also the number of all conjugation classes in the group of permutations on n letters. Now, if we look at the left non-degenerate solutions, they have the same form as the right non-degenerate ones, except that the self-map is no longer assumed to be bijective. So the number of isomorphism classes of all left non-degenerate Frobenius separability type solutions on a set with n elements is this time equal to another classical combinatorial number, namely the Davis number. A few words about this Davis number. So we have an action by conjugation of the symmetric group on the set of all set functions on this set with n elements, and the Davis number is counts the number of all conjugation classes of self-maps on a set with n elements. It is also known as mapping patterns or mapping types, and this is how it appears in the work of de Bruijn. And it was again, de Bruijn, who gave the explicit formula for computing d of n that you see on the screen. It's rather complicated in general, as we can see. Now, if we look at solutions of Frobenius-Separability type, which fulfill other conditions usually imposed in the literature, and try to compute the number of isomorphism types, we will again find that other classical combinatorial numbers are involved, and even graph theory in certain parts. I will show you a few more easier examples for now. For instance, if we consider the involutive Frobenius-Separability type solutions, then the number of isomorphism classes of all involutive solutions equals the number of divisors of the cardinal of n. Then for the idempotent Frobenius-Separability type solutions, the number of isomorphism classes is again Euler's partition number. And in the case of unitary Frobenius-Separability type condition, the number of isomorphism types can be computed by this formula, where, of course, this notation denotes, as usual, the integer part of the real number. Now, another important class of solutions is that for which the projection on the first or the second component is surjective. This also includes the solutions for which the first component is bijective. And the first thing that we can prove about this class of solutions is that they are decomposable. We can even provide a characterization for such solutions. So if we assume R to be a Frobenius-Separability type solution for which the projection on the first component is surjective, then we can find two non-empty sets, A and B, and the self-map omega, such that our solution R is isomorphic to a solution of this form, right, on n times B. Namely, the solution switches B1 with B2, and then it applies omega on the second component. And all these rely on some results on the structure of Kimura semigroups. And I should also point out that with the exception of A being a singleton, all solutions of this form are not non-degenerate. Moreover, based on the theorem from the previous screen, we can again compute the number of isomorphism types of all Frobenius-Separability type solutions on a finite set with n elements, such that the projection on the first component is surjective or even bijective. In both cases, the number is a sum over all divisors of n and involves, in the first case, the Davis numbers and the Euler partition number in the second case. As I mentioned, some other some other combinatorial numbers will appear. This is the case if you look at the number of isomorphism classes of all Frobenius-Separability solutions of finite order on a set with n elements. This is given by the formula on the screen, where this G of D is the so-called Landau number, and there is also this other notation which I will explain together with the Landau number in a bit in the next slide. So the Landau number is defined as the maximum order of a permutation in Sn. There is only an asymptotic formula for computing it, and it is written on the slide. And then this second term that we had in the sum from the previous screen denotes the number of all conjugation classes of permutations of order k in the symmetric group Sn. And these are the two papers where you can find most information on the Landau number and maybe some asymptotic formulas and other properties. Now, if we look at indecomposable non-degenerate solutions of Frobenius-Separability type, we find that up to isomorphism, there's only one such solution. If we consider right non-degeneracy, and by contrast, if you look at indecomposable left non-degenerate Frobenius-Separability type solution, then the number of isomorphic classes is the Harary number of n. Now, in order to explain this Harary number, we need to take a very short graph theory detour. So first, a directed graph associated with a self-map is the directed graph whose vertex set is x, so the set x, and it has an edge between x and y precisely when y equals f of x and x is different from y. So in other words, you consider the usual graph of the map f, so the set of pairs x and f of x minus the diagonal. And I wrote here almost Harary because a similar definition appears in the work of Harary under the name of functional digraphs in the paper that you see on the slide. However, Harary's functional digraphs are those directed graphs in our terminology for self-maps with no fixed point. So he does not allow fixed points from the very beginning. And in this setting, we can prove that the functional digraph on a self-map is connected in the usual sense, meaning that any two vertices can be joined by a path, disregarding the edge orientations, if and only if there is no non-trivial F invariant partition of F. And this is as well equivalent to the existence for any x and y of two non-negative integers m and n satisfying this condition. And we will call a map F satisfying one of these equivalent conditions connected. And now this Harary number is precisely the number of conjugation classes of all connected self-maps. This Harary number also makes an appearance in the paper by De Bruijn that we've seen earlier, relating it back to the Davis number via the formula that you see on the screen. The last part of my talk will be devoted to studying the automorphism groups of Frobenius-Separability type solutions. And I will start by introducing the following terminology. So the centralizer or automorphism group of a family of cell maps on X is defined as the set of all permutations on X which commute with all self-maps in this given family. In the special case of only one map, so if you start the family consisting of just one map, we call it the functional centralizer of F, and it will be denoted like this. Now, the motivation for introducing this centralizer to begin with is the following. I remind you that the left non-degenerate Frobenius-Separability type solutions are of this form, right, for a certain self-map F. And it can be proved that the automorphism group of this class of solutions, the left non-degenerate ones, is precisely the function centralizer of the corresponding cell function F. Now, the converse also holds. So we can prove that any function centralizer is in fact isomorphic to the automorphism group of a left non-degenerate Frobenius-Separability type solution. Now, if you look at solutions of Frobenius-Separability type, whose projection on the first component is surjective, and this includes, for instance, finite order or unitary solutions, then their automorphism group is isomorphic to the direct product of a permutation group on a certain set X and a function centralizer group associated to an endo-function on another set B. And a question which comes naturally in this context, but we could not yet solve it, is the following. Can we prove that any group is isomorphic to an automorphism group of a Frobenius-Separability type solution on a given set X? We could find a result that is close to what we want, but still does not solve our problem. And it is contained in the book that you see on the screen. And more precisely, the result that I'm referring to, it proves that any group G is isomorphic to the centralizer of two functions on some set B. So this is the closest that we came to the open problem that I've mentioned. What we could prove instead is that for any group G, there exists a Kimura semigroup, a permutation action on some set C together with permutation groups for each element of C, such that the automorphism group of X is isomorphic to a semi-direct product between this direct product and the group G. So in other words, we can say that G, so the group G, any group G is isomorphic to a split quotient of the automorphism group of X with kernel, again, this direct product of groups. On the other hand, we have some examples of groups, or other classes of groups, which are not isomorphic to a functional centralizer group. For instance, we have finite group admitting no surjections on the non-trivial cyclic groups, and there is also a class of Kimura semigroups with the same property. So what we can definitely say is that the class of automorphism groups of Frobenius-Separability solutions is strictly broader than that of function centralizers. Now, in the case of abelian groups, things are maybe less complicated than in the arbitrary case, and we can prove that those abelian groups, which are functional centralizer groups, are precisely the direct products of cyclic groups. Okay, and I will stop here. Thank you.
Thank you, Anna, for your nice talk.
Thank you.
Other questions? Oh, there is in the chat. Do you want to ask a question, Florin? There is a question in the chat, Anna. Can you understand it?
I'm not really sure what the question is. So it says, please refer to vector spaces if possible. my talk was on the set theoretical solutions of Yang-Baxter equation. What we can say about the quantum version of it is that it's of course more difficult to deal with than the set theoretic one. It is the reason why the set theoretic was introduced, to give maybe a more general and easier approach to constructing linear solutions. But as far as the quantum version of, so the linear version of the Yang-Baxter equation goes, not much is known, except for maybe the famous FRT theorem, which I mentioned in the beginning, which is very general in nature, but it doesn't really say much when it comes to really trying to write down and count the number of solutions. I'm not sure, is that what you were looking for, Florin, or? Okay.
Okay, thank you. Some more questions? Okay, thank you very much, Anna, for your nice talk.
Thank you.
And I also thank all the participants and wish you all a good week. See you next Monday.
Thank you. See you.